In this lecture, we are going to really apply the L'Hopital's rule to compute limits of indeterminate forms. So if we have a limit of a quotient which is an indeterminate form, 0 over 0 or infinity over infinity, then we know that from L'Hopital's rule that the limit of the quotient is the same as the limit of the quotient of the derivatives. So you can, if you know it's an indeterminate form of which kind, you can't know it's an indeterminate form unless you know which kind, right? So you need to know, okay, you need to see that I'm getting a 0 over 0, or I'm getting an infinity over infinity. Then you say, okay, I'm going to apply L'Hopital's rule. I differentiate the numerator, you differentiate the denominator, and see if the new quotient has a limit. It is true not only if the right side end up with a limit, but also if the right side turn out to be negative infinity or positive infinity. Now let's look at examples. As I said, this whole lecture is about how we are going to apply L'Hopital's rule to find more limits. So pretty much today's task is to find limits. Okay, first example. When you plug in x equals 2 in x squared minus 4 and x squared minus 5x plus 6, you are going to have 4 squared minus 2 squared 4 minus 4, 0, over 2 squared 4 minus 5 times 2, 10, negative 6 plus 6, 0. So you are getting 0 over 0. You need to know which kind you have to say I'm using L'Hopital's rule. The limit stays here, and you differentiate the numerator, x squared minus 4. X squared give you 2x minus 4. Differentiate, you lose it. X squared, again, 2x minus 5x minus 5. This time, if I plug in, I will have 4 over 4 minus 5. I get two numbers which none of them are 0. So I'll really do the plugging in 2 times 2 minus 5. See, you really need to do it anyway. You need to do that direct plugging substitute anyway. It's just that if it turn out to be 0 over 0, you'll say, okay, another round of L'Hopital's rule. Or, good, it's not 0 over 0, then you have your conclusion. So here I have 4 over 4 minus 5, or 4 over negative 1, and that's negative 4. On the other hand, question 2, I have the same expression, same quotient, but this time x approaches infinity. When x approaches infinity, x squared goes fastest, then the x, so it's infinity over infinity because I have x squared and x squared. Then I'm differentiating the top and the bottom. I end up with the same thing. But this time, when I plug in 0, 2 times infinity is still infinity. 2 times infinity minus 5 is still infinity. I'm still having the indeterminate form infinity over infinity. So I'll do it one more round. This will be the limit as x approaches infinity, 2 over 2. Now, there's no x anymore. And of course, that's 1. Keep going. This time I'm making x approaches 4. When x approaches 4, I'm having the numerator 4 squared minus 4. 4 squared, 16 minus 4, 12. Denominator 4 squared, 16 minus 5 times 4, 20 plus 6. So none of them are 0, which means you cannot use L'Hopital's rule. Okay, if you say you use L'Hopital's rule, it will be it will be 2x over 2x minus 5. And you plug in Well, actually, it depends on whether you plug in or not. If you don't plug in, it will go back to 2 over 2. If you plug in now, it will be 8 over 8 minus 5, 3. But of course, that's wrong because the real answer is you just directly plug in the 4. You will have 16 minus 4, 12 on numerator. This is 16 minus 20 plus 6. That's 22 minus 22. So actually the answer is 6. Okay, that's why I keep saying you need to know which kind of indeterminate form you have, which means you really need to know I am having 0 over 0 or I am having the infinity over infinity. Then you apply the L'Hopital's rule. Okay, next I have x approaches 3 from the positive side, a single side derivative. Plugging in 3, I'm having 3 squared minus 4, which is 5 on the numerator. But the denominator, I'm having 9 minus 15 plus 6, which is 0. So I'm having a 9 minus 4, 5 over 0 situation. Not 0 over 0. I can't use L'Hopital's rule. Okay, so we go back to our old way. Factor the numerator and factor the denominator. You will see that common factor. So it turned out to be x plus 2 over x minus 3. And this is why I gave you a single side limit, because I wanted to end up with infinity. So x approaches 0 from positive side. That means on the numerator, I'm having 3 plus 2, but on the denominator, I'm having a 0, but like positive. So I'm having 5 divided by a really large number. Really small positive number. It will end up with a very large positive number. So infinity. Okay, now you can pause the video and try practice number 1 through number 4. Pretty much same thing. Use L'Hopital's rule. Here, I have a bunch of remarks for you. First of all, I can't emphasize this enough. You have to make sure you are having 0 over 0 or infinity over infinity. Then you use the L'Hopital's rule. It does not work when it's not an indeterminate form. I just showed you in question 3 where, x approaches 4, right? Also, for any positive real number a, pretty much statement 2, remark 2 is telling you e to the x. As x approaches infinity, e to the x grows faster than exponential function grows faster than powers. That's why they, when they try to say this grows so fast, they say it grows exponentially because it does grow faster than powers. But on the other hand, any power, no matter how small the real number is, as long as it's positive, it still grows faster than log. Okay, so that's like how, if you understand how, which one goes faster, maybe you can save yourself some time for the L'Hopital's rule and just say, okay, it's exponential over power, so it's infinity, or power over exponential, that's 0. Kind of shortcut. There are other indeterminate forms that we didn't talk about. When we still have the product, the difference, and the powers. So we are still using the L'Hopital's rules to deal with them, which means we are going to make all of them quotients. The first, when you have a product, when 0 and infinity, these are the limits of the two factors, make it a quotient. So pull one of them to the denominator. It doesn't really matter. You pull the first factor or the second factor, but f times g equals f over 1 over g. This is what I meant. I can't type it this way. It will be super ugly. Okay. Again, it doesn't really matter whether you do this or you keep the second factor and pull the first factor to the denominator. Either way, you want that quotient, and taking the reciprocal of 0, you get infinity, or taking the reciprocal of infinity, you get 0. So they will turn out to be 0 over 0 or infinity over infinity. Subtraction actually is the hardest. If you have a difference, you need to somehow convert it into a quotient. So you need to make it a fraction with the denominator so that you can use the L'Hopital's rule. This is the trickiest, in my opinion. It's very hard to see sometimes. Then all the powers. So with powers, we sort of use the same technique. We are going to take log on both hand sides of, take log on the power so that it become a product of the exponent and the log of the base. L'Hopital rule that by, again, it's a product, you pull it down, pull one of the factors down. Okay, so log y will be g times log f, then you pull the g to the denominator, log f remains over 1 over g. That's how you are going to compute all the indeterminate forms with other kinds, other than the ready-to-go quotient form. Okay, more computation. The first one, the limit as x approaches infinity of x squared times 2 to negative x. As x approaches infinity, x really large, x squared will be really large. So I don't want to write down all these. Oops, sorry. So x squared goes to infinity, but 2 to negative x, that's how power looks like, right? So when x approaches negative infinity, the power goes to 0, goes to 0. You do have infinity times 0 case. You need to take off the graph. So what are we going to do? This one is so natural, x squared times 1 over 2 to the x. It's a negative power, so naturally you pull that thing to the denominator, 2 to the x. And that is infinity over infinity. You differentiate both of them. Numerator turns out to be 2x. Denominator, you get a log 2 times 2 to the x. X approaches infinity, that's still infinity over infinity. One more round. You can see that the numerator is not infinity anymore. And the denominator differentiate the 2 to the x, giving you another log of 2 times 2 to the x. Now it's not infinity over infinity. This is really 2 over infinity. That's 0. Anything over infinity is 0. Example 2. As x approaches pi over 2 from the negative side, we have the difference of secant minus 10. I don't know if you know what secant is as x approaches pi over 2, but secant is 1 over cosine. Cosine as at pi over 2 is 0, so it's really 1 over 0, which is infinity. And that's why you need a negative side or positive side. So this is in positive infinity, and 10, I hope you know, looks like this. So that's another positive infinity. We are having infinity over infinity case. And naturally, pi over 2 negative, secant is 1 over cosine x, 10 is sine x over cosine x. And that gives you the numerator. X approaches pi over 2 from the negative cosine x on the denominator, 1 minus sine x on the numerator. At pi over 2, sine the 90 degree is 1. 1 minus 1 is 0, and pi over 2 is 0 for a cosine. We talked about it. So we have 0 over 0 situation, then we can differentiate limit x approaches pi over 2 from the negative side. Quotient 1 is gone, taking derivative, you have negative cosine x over cosine x taking derivative negative sine x. I can cancel the negative signs. As x approaches pi over 2, here's pi over 2, 0, 1, cosine, sine. So this is really cosine over sine, 0 over 1 now. And which means you can plug in directly 0 over 1, which is 0. The third example is a power, and this is where we are going to use the logarithmic. Not really differentiation, but you use log to pull it down. So let y be the power that you are dealing with, then log y will be log x to the x power, and you pull the x to the front. And then you turn it into a fraction. But before that, let's make sure x approaches 0 from positive direction. This log will be as 0 times x approaches 0 from positive direction, you are getting a negative infinity. So this is an indeterminate form. This will be the limit x approaches 0 from positive, x times log x, and I will need it to be a quotient. I guess it's nicer to have 1 over x than 1 over log x. So this time we are really having 1 over x, 0 over 0. Then I differentiate both. Log x give me 1 over x. This is x negative 1 taking derivative negative x negative 2. So this is actually, this is x negative 1. So x negative 1 over x negative 2 actually give you x. This is negative x. And as x approaches 0, x approaches 0, and negative 0 is still 0. Oh, sorry, I shouldn't box it. I'm not done. So I know that the limit of log y is 0. That means y is e to the 0, 1. Okay, log y is 0, then e to log y. So essentially y is e to log y. Goes to 1. Sorry, I should have the limit here. Otherwise, it doesn't make sense. Okay, last example for this lecture. I'm having the limit as x approaches infinity 1 plus 1 over x to the x power. This is really a 1 to infinity case. The base, as x approaches 0, 1 over x goes to 0. Sorry, as x approaches infinity. As x approaches infinity, this goes to 0. Right? So the whole base goes to 1. While x, the exponent goes to infinity. So this is 1 over infinity case. 1 to infinity power case. Again, the whole thing is y, so that I can log it and pull the exponent to the front. And we know that it's 0 times infinity case. Same thing, I will pull the x to the denominator because 1 over x is nicer than 1 over log 1 plus x, 1 over x. You know, the alternate will be x over. You'll see how I don't want to differentiate this and this, especially the denominator. So I'm not going to do this. Okay, now the limit as x approaches infinity log y will be the limit as x approaches infinity. I rewrote it this way. And because x goes to infinity, 1 over x goes to 0, log 1, and log 1 is 0. Log 1. And on the other hand, x approaches infinity, 1 over x goes to 0. I have 0 over 0. Then I differentiate the top. I'm having 1 plus 1 over x is x over x plus 1 over x, so x plus 1 over x. Because taking derivative, I need to flip it, x over x plus 1 times the derivative of x 1 over x would be negative x negative 2. And on the other hand, the denominator is only 1 over x. Taking derivative or x to negative 1, the derivative will be, again, negative x negative 2. Because this is x negative 1. They cancel each other because they are the same. Even the negative signs cancel each other. So I really end up with the limit as x approaches infinity, x over x plus 1, which turned out to be an infinity over infinity case. I differentiate it one more time, 1 over 1. That's 1. So the limit of x approaches infinity of y will be the limit x approaches infinity e to ln y. And that's e to the first power, or e. And what I'm trying to show you here is not only that this 1 to infinity power has a limit, but also that limit is e. So this formula, that's one of, as I introduced when we did e and log one more time. E has many definitions, and the limit of this will be one of them. So pretty much this is 1 plus 1 half, second power, and then 1 plus 1 third, third power, 1 plus 1 fourth, fourth power, where the base gets smaller and smaller, but the as x approaches infinity, of course, this is how it goes. You have smaller and smaller base, still bigger than 1, but the little bit that bigger than 1 gets smaller and smaller, but meanwhile you have more power. And this list of numbers actually goes to e. Okay, that's all for today, and you can finish the practice number 5 and 6.